No, seriously, so, you've had a lot of the internal resources have moved from servers, Corvo, RPC, that are difficult to manage, and have actually been we'll just do it all in XML and all will be well. It turns out that it's actually dramatically reduced the parsing load, and so things are a lot easier. The problem is they're so much easier, they put in so much more crap because it's so easy to put in just one more schema element. So yeah, web services are a big old mess. And with the web plugins, you now get to bounce across into the corporate network and play with the internal web services. The final level of access are the sockets, and that's where I'm going to spend most of my time because I don't want to be limited to anything. I just want to bounce off your web browser and get to your file servers. Speak MySQL, speak SQL servers, speak SMB, speak RPC, speak NTP, whatever the heck I happen to feel like. It turns out Flash will give you arbitrary TCP access. In Java, TCP, and we'll throw in some UDP as well. Let's talk about what plugins are actually giving us. Java. This is a very instructive example because Java was the original target of the 1996 Princeton attack. From what they did after realizing, wow, it's 1996, but security actually exists. They did the right thing. They totally locked down the applet interface and made it so that the applet had to download the content itself, and because the applet downloaded the instructions, it knew what IP address it came from, and because it knew what IP address it came from, it would only attach the right IP to the right content. Great. The problem is that there was a totally separate way you can instantiate Java objects. So they put in this big, great wall that has stood for 11 years, and they put a little door over here. You just walk around. Okay, thank you. It's called Live Connect. It does not work in Internet Explorer. Who knows if that's intentional? But it does work in Firefox and Safari, though. And, it's totally rebindable. You just get to start up a Java object from within JavaScript, and Java has no idea where that JavaScript came from. It just gets a blob. Hey, can you open a socket? Okay, thanks, bye. Yeah, they're screwed. So, but it doesn't work in Internet Explorer. What does work in Internet Explorer is Flash. And this is sad. They tried so hard. Probably the most work going on in the industry right now to do cross-site scripting stuff securely. The people who are actually thinking hardest about how to actually do these complex security models, Adobe's doing a really, really good job of this. And they built this entire huge framework for XML documents that describe security policies. And unfortunately, that XML stuff is also vulnerable to DNS rebinding as well. So you get around the security policy by using the same attack. The effect sucks. You get arbitrary TCP access. You have to do some tricks to get below port 1024, as if that meant anything anymore. Who in this room thinks ports below 1024 is at all a security use at all? Okay, so here's the deal. Traditionally, the idea was, okay, users will use servers on ports above 1024. Administrators below 1024. Now you'll be able to differentiate a user-started service from a system-started service. This seemed like a great idea at the time. And then you look at ports like, RDP, above 1024, MySQL, above 1024, SQL Server, above 1024. Turns out there's a crap ton of really useful stuff that's above port 1024. So it's a kind of a useless security mechanism now. So, mechanisms for rebinding address. How do you actually get Flash to see motion from, okay, download this movie from this address, get this security policy from this address, but now, only now should you go ahead and go over there. How are we going to do that? Alright, we got 3 ways. First way is what's been commonly known, the other 2 I'm bringing to the table. So, the first way is called temporal modulation. When you get a record back from DNS, it's got a time to live. It says, this value you should hold on to for this many seconds. And that value could be 0. And what happens is it says, oh, okay, the first time you look it up, you get an address. The second time you look it up, don't cache it, it might have changed, get an address. Third time, don't cache it, it still might have changed, go look it up. This happens to be the exact functionality that we want to abuse. We want you to look it up at time A and go to the server in Europe, and time B and go to the printer down the hall. So we'll just use it for what it's meant for. And so you get these networks, they brag, oh, we've solved this problem for years. We say records have to last at least 5 minutes. Because you know, hackers just can't wait 5 minutes to break into your network. But alright, you want to play that game, it turns out we got 2 more. Guess what else you can do in DNS? You can return 2 records at the same time. Yeah, so basically when you look up bar.com, it returns both the address out in Europe and the address to the printer down the hall. Now there's a bit of a problem. What if the browser picks wrong? You know, sometimes you want to go to one address, sometimes you want it to go to the other. What if the browser guesses incorrectly? Well, I've got this really crazy, awesome hack. It's called trying again. Amazing how well that works. And I'm not going to go too hard into how the trying again works, but here's a big messy slide that tells you how to try again. So, people are trying to use DNS TTL as security technology. They were never designed to be a security technology. Things always die when you decide to turn one into them. Finally, we have something less a security technology than virtual machines. So I used to call this Tommy the Tank Engine security. I think it's safe, I think it's safe, I think it turns out that's the wrong tank engine that says that. No, it's actually, and I'm not joking, the pony engine that says that. Wow. So it turns out overriding a TTL when you actually own the record at play is trivial. It's by design. Here's how you do it. So, when you look something up in DNS, you do not necessarily get back an address directly. Oh no. You can get something called a CNAME. That says, I know you looked up bar, but bar's just an alias, man. That's actually 2.bar, and here's 2.bar's new address. It turns out, and here's its new address, actually overrides whatever was in the cache, regardless of TTLs. Works like everywhere. So here's what it actually looks like. We're going to look up one.foo.notmallory.com, because you know the server's totally not Mallory, it's totally not malicious out to hack you. You can tell because it says it's not Mallory. Right, so we're going to look up one.foo.notmallory.com. And it's going to reply and it's going to say, nah, you didn't mean one.foo. You meant bar.foo.notmallory.com, and here's its address. And indeed, when you check the cache, you'll say, okay, bar.foo.notmallory.com, 9 seconds ago, 120 minus 111, 9, I can do arithmetic. Bar.foo is going to go to 10.000. Sweet! This should be valid for another 111 seconds. Unless we look up 2.foo.notmallory.com. And it as well is going to say, no, you meant bar.foo. But here's bar.foo's new address, just so you know. Now, when we look it up, oh, look, it has immediately rebound to a new address. Sweet. I hope you enjoyed that 5-minute limitation of yours, because it totally broke. So, review. By swapping addresses out from underneath the web browser, we can get arbitrary TCP and sometimes even UDP access to hosts reachable by the client. What can we do with this? Ah, hell. Can we VPN into corporate networks using nothing but a lowered web browser? Sure, it's easy. Okay, it's a total pain in the ass. It takes like 7 programming languages and 6 protocols. What is it with the web designers out there? Every time you blink, you're in a new programming language. Totally easy. Alright, we got 3 actors in this little dance. We got a browser. Browser's got access to internal resources. We got an attacker. The attacker wants access to these internal resources. And then we got the proxy. And the proxy is going to hook the browser up to the attacker. And the software I've written to do this, and the name will make sense in a while, is called Slurpee. Slurpee is a multi-point protocol server built using the Perl object environment. Very nice, non-blocking, supports one server with lots and lots of different protocols that it handles. And it turns out what we need to do, the attacker is going to give us TCP streams that need to be sent off through the browser. The browser is going to pull down these TCP streams over HTTP. Remember, right? So the deal is that the browser is like a network stack that you get to give code to. This is awesome. Slurpee's got to handle DNS. All those crazy DNS tricks, yeah, Bind ain't doing that. So we need to have a Slurpee run DNS. And because there's some security policy stuff that Flash handles, called an XML socket, we got to put in a server for that too. That wasn't a big deal. The basic theme is the attacker connects to the proxy, which manages the appropriate resources in the browser to service the attacker's connections. Now, what we do is we build what I call a bucket of sockets. The browser connects. It establishes an iframe called a bucket. The bucket holds for new connections to establish. And usually there'll be nothing there. But you know, eventually the attacker's going to have something he wants. And be like, I want to go to 10.0.1 port 80. And the attacker's going to register with the proxy and say, hey, give me access to this. Browser is going to come to the proxy and say, hey, you got anything for me? Proxy's like, yeah, I got something for you. Give me a connection to 10.0.180. Now the browser spins up a second level iframe. It is stored, this original iframe is the bucket. And each of the child iframes in there, that is the socket. It's like a socket, but it sucks. Now, the bucket comes from, whatever site, bucket.malware.com. But each of these sockets comes from a dynamically addressed site, address. In this case, say 10.0.1 foo Now that doesn't mean it resolves to 10.0.1 yet. It just will at some point in the future. This second level iframe is called a socket. You're going to note, by the way, this is a very obtuse design. It's obtuse intentionally. People have proposed some really bad ideas for solving this problem. Like ideas that laughably don't work. I've just silently made all those bad ideas fail in this design. So, what does it actually look like? Anyone hear about JSON in this place? JSON is like XML, but significantly less hideous. JSON is basically, you get the same results of XML, but you just evaluate it in JavaScript or parse it in JavaScript, and it just works. You now have this huge, this would probably be like 5 slides in XML. Very small in JSON. But what it looks like is that the proxy is going to say to the attacker, hi. You have a connection, you're going to have a set of connections to 10.0.1. Connection 3 in there is going to have some sequence numbers, some acknowledgement numbers, some data to the browser, some browser state, some server state. Okay, fine, I ported TCP to JavaScript. What? Saturday night. So, the ultimate question, how many DNS requests does it take to get to the center of your corporate network? Well, we can't use JavaScript alone. The proxy can cause the browser to open up a socket, and the socket's an iframe. But what's going to happen in there? Well, JavaScript can't do it. We need to get a Flash object. We need to basically drive the Flash object with JavaScript. Now, there is some way to do this right in Flash somehow, but it turns out there's a really cool language out there called Hax. It's called Hax. I have to use it. It's a meta language. You can compile it down to Flash and JavaScript, and you can actually use Hax objects compiled to JavaScript from JavaScript, and the Hax objects can call their Flash equivalents. So Hax is actually a fantastic bridge between Flash and JavaScript. So I ended up writing all my stuff to it. So what I do is I compile a Flash movie. First off, the browser has to load the movie. And that's going to be loaded from 10.0.1